Okay, so hi everyone. In last class we saw like basic Boolean algebra. We did work with proposition and all. We saw and or function and we did some problems. Today we'll work on bits basically. So we'll basically be working with numbers one and zero. These are called bits. So or you can also call them Boolean, I think. And there are some operators defined on them, just like you have plus in your integers, right? So they have there's a Boolean operator called plus, which works a similar way. So the way plus is defined is 0 plus 0 will be 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1. Instead of like you'd expect 1 plus 1 is 2, right? But the only integers you have defined is 1 and 0. So 2 is not defined in this thing. So it cannot be 2. But if, for people who know what a bit, what like how binary works, it's like 1 plus 1 is equals to 1, 0, they say, right? But the thing is, here we want to preserve the number of bits which we are dealing with. Like the operator plus, we want that it gives, if it takes uh, like one bit on both the sides, then we would want that it outputs one bit as well. So to maintain that, we give 1 plus 1 equals to 1. And also, if you see that plus works similarly to or, you just consider 1 is true and 0 is false. And similarly, you define multiplication. The multiplication is same as integers. So like 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. And this works like and operator. And then this is, I think this is called complement. Oh, wait, I forgot the word for it. I think I heard somewhere.
Subtraction?
No, it's called complement. Subtraction is not defined. I'll tell why. Uh, so it's called complement. Complement is like the negation operator in propositions we had, right? So like 0 complement is 1, 1 complement is 0. Okay, so once you have integers, how do you define subtraction? It's like you add a negative number basically, right? So if you have addition defined, this means subtraction is defined using addition, right? But in this case, there's a slight issue. So suppose you have, uh, let's say, okay, let's consider one second. Okay, so let's consider 1 minus 1. So you would expect this to be 0, right? Which means that 1 should be equals to 0 plus 1, which is 1, which is true. But suppose we assume, like, what's wrong with 1 minus 1 equals to 1? This is like 1 equals to 1 plus 1. But by the way we are defining our addition, 1 plus 1 is just 1, right? So this should be true. So like 1 minus 1 can be 0 or 1 both. So it is not a valid function. So in this case, subtraction is not defined. Does that make sense?
Yes.
Okay. So yeah, these are the basic Boolean operators. Now let's see what a Boolean function is. So I cropped the definition, but let's just ignore this for a second. Sorry, let's just see. So the variable x is called a Boolean variable if it assumes value only from b. So if x is a variable which can take value 0 or 1, then we say x is a Boolean variable. Consider b of n to be the set of all tuples of length n such that each xi is basically a Boolean variable. So this is a tuple of n Boolean variables. Now, like if you see the b of bn has 2 to the So if you see B of n has 2 to the power n elements, because x1 has two options 0 or 1, x2 has two options 0 or 1, and xn also has two options 0 or 1. So in total there are 2 to the power n elements in the set Bn. And we define a function f from B of n to B. B is 0 comma 1, and this function f is called a Boolean function of degree n. So this was like the way you define it rigorously, but let's see what it means. So let's consider this function f of x comma y equals to xy conjugate plus, let's say, x conjugate. X, y conjugate, x conjugate, xy conjugate, and then you'll have f of x comma y. Okay. 1100 0011 010 0101. Xy conjugate. Oh, sorry, this is product. So 0 1 0 0, and then you take addition 0 1 1 1. So this is a valid function, right? Like it is in 2 degrees. Okay. So yeah, like the output, it takes only 0 or 1, and it's defined from uh like is it in degree tuples? How do I say that? Okay, you can write this thing as x conjugate y plus x conjugate y conjugate. I'll explain why this is equivalent, but this function will also give you the same output. So if you see that each of the terms here is like a function of, okay, this is hard to explain in terms, but it's basically the same as normal function in like multiple variables, basically. That's what it is. And the output should be 0 or 1. Is that a convincing enough definition of what a Boolean function is?
I think so, yeah.
Okay. Also, Shresh, you just joined, right? So, do you know what? So I'll just quickly review.
Yeah, I followed.
Okay, nice. Yeah, just one thing that might be useful is the plus operator is defined this way: 0 plus 0 is 0, 1 plus 0 1, 0 plus 1 is 1, and 1 plus 1 is also 1. It's not
Yeah.
1 0. Yeah, cool. So this is what a Boolean function is. So let's consider this thing. Prove that x plus yz is equals to x plus y times x plus z. Try to do this. Take a minute or so. X, y, and z are Boolean variables. If y is equals to 1, okay, let's see. If y equals to 1, then this side becomes x plus z, and the other side is x plus 1, but x plus 1 is always 1. So
Yeah.
it's just 1 times x plus z, which is x plus z. Cool. What if y is 0?
Then the left hand side is x.
Yeah. And the right hand side?
Wait. Yes. If x
Yeah.
is zero, then right hand side becomes both become zero, and if x is one, then both become one.
Yeah, you consider these two. Cool. Yeah, this proof works. This is basically the same as constructing a truth table, but you're basically just
Yeah.
ignoring the z thing
Yeah.
because you do not need that. Uh, Another way to prove this is like okay, like the correct way to prove distributive law is this thing, the one which Shresh said. But let's just assume distributive law. What will this give you? X plus y times x plus z is equals to x times x plus x times y plus x times z plus y times z, right?
Right.
X times x is x. Because if x is 1, then 1 times 1 is 1. If x is 0, then 0 times 0 is 0. So x times x is just x. Plus x times y plus x times z plus y times z. And then you can take the x common. So you'll have 1 plus y plus z plus yz. And then 1 plus anything is just 1. So this is x plus yz.
Acha, nice.
This is all. Do you follow?
Yeah.
Okay. Kachi, do you follow?
A bit, yes.
Okay. So yeah, this is one cool idea that I wanted to keep put in notice that whenever you see something like a times a, then it's good to consider a, or other way around as well. So like in some proofs, you need like you have given a, but you have to consider a times a. And similarly, if you're given a, it's wise to consider a plus a as well, because a is equals to a plus a. So if a is 0, then this is 0 plus 0, which is 0. If a is 1, then this is 1 plus 1, which is again 1. So you can consider a equals to a plus 1. Or if you want, if you have 1 sometimes, you can just write 1 as x plus x conjugate. So these are some things which you can consider while doing proofs, which will be helpful in problems.
Okay.
So yeah. So let's see what do we mean by graphical representation. This effectively works only for like Boolean function of 3 degrees at max. So what it says is we can represent a Boolean function graphically by distinguishing the vertices of the n cube that correspond to the n tuples of bits where the function has value 1. So let's consider this function x, y, z f of x comma y comma z. 1, 2, 3, 4, 5, 6, 7. So 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0. I'll just put 0 and 1s here randomly, does not really matter. 0, 1, 1, 0, 0, 0, 0, 1. So this is a function in 3 degree. So you consider a cube in 3 degrees, n cube. Uh, okay, this is sort of hard to draw like this. Yeah. Let's call this as x, y, and z. So this point becomes 1 comma 1 comma 0. This point is 0 1 0. This point is 1 0 0, 0 0 1, 1 0 1, 0 1 1, 1 1 1, and this is 0 comma 0 comma 0. So what we do is wherever the function is 1, we distinguish that point. So we can like just mark it with a different color. So it's one. I see it's 1 at 0 0 1. So I can mark this blue. 0 1 0. I can mark this as blue, and then 1 1 1. Okay. This. So yeah. Okay. Yeah. So this is how I graphically represent this function, which I have written here. And for a 2 degree function like in x and y, you can just consider a square and then mark the points distinguishedly. The reason why this effectively works for 3 dimension only, because we obviously cannot perceive 4 dimensions. So we cannot really see graphically how the function looks like. So It's sort of a silly thing to do this because for 3D grid it's not really useful because it's not much to like just write it down. Like it's just 8 things. So yeah, but this exists, so I thought why not include it. Okay, duality. Oh, by the way, Kanav, just to tell you, this is how we define the plus function. The other thing should be clear to you. 1 plus 1 is defined as 1, by the way, not 1, 0 or something.
Yeah, fine.
Okay. So let's say duality. So in duality, what we do is wherever you see a product, convert it to plus, and wherever you see a plus, convert it to product. And yeah, wherever you see a 1, convert it to 0, and wherever you see a 0, convert it to 1. This is how you define a dual. So suppose you have this function f of x comma y comma z, not just y, z, let's say x comma y, which is xy plus 1 times x conjugate plus y. So the dual of this, it's represented by like f to the power d, by the way, dual. So see, let's first write the dual of this term. It's x times y, so it becomes x plus y, and then it's plus 1, so it becomes product with a dual of 1 is 0, 0, and then the product here will become a plus, and these two terms are in summation, so this becomes product x conjugate y. So this is the dual of this thing. Is the definition of a dual clear? Like how we define dual of functions? Yes or no?
Yes.
Yeah.
Cool. So the point of this is if f x1, x2, so on till xn is equals to g x1, x2, so on till xn, then dual of the function f is same as dual of function g. Uh, this helps us prove some new identities. Like just before we saw x plus y times x plus z equals to x plus yz, right? If we take dual on both sides, the dual of this becomes xy plus xz is equals to uh, x times y plus z.
Wait,
So
I have a doubt. Is the converse also true?
what do you mean by converse?
Like if two functions have the same dual, then they will be the same. It should be
Yeah.
right because dual of a dual is the same function.
Yes, exactly. Yeah. So this is why duals are useful. I won't be proving it right now. We'll see if we have time at the end of the class, and then we'll prove it. Otherwise, I'll give you a few hints, and then you can prove it on your own. Okay. So is that, and this thing is called duality principle. So is duality principle clear?
Yeah.
Okay. Let's move on to some. Okay, let's see. Okay, cool. Yeah, I'll do that. So that minimization is on. Yeah, after this thing, minimization will do, which will be more fun. So a literal is basically just a Boolean variable or its complement. It's like x or x conjugate. This is a literal. And a minterm of the Boolean variables is basically a Boolean product of n. Like minterm is defined for like Boolean function of n variable or n degree. So we take product of the different n variables that you have, where each of the terms is a literal, which means that yi is either xi or xi conjugate. So hence a minterm is product of n literals with one literal for each variable. So the purpose of writing minterms is, let's consider n equals to 5 and let's write this minterm. x1 conjugate times x2 times x3 conjugate times x4 conjugate times x5. Can someone tell me what is the value of this thing? Like if I consider this as a function, then how does this function look like?
Mm, I don't know.
Shrish, yeah, go on.
No, I don't know. Nothing.
Okay. Kachi, do you have any idea? Guesses are also fine.
Nothing so far.
Okay. So basically I just want the value of this function when I plug in different values of x1, x2, x3, x4, or x5. So see, this function will be 1 because these are products, right? If and only if x1 conjugate equals to x2 equals to x3 conjugate equals to x4 conjugate equals to x5 equals to 1. Like apart from that, if any one of these 5 things is 0, then the
Acha.
whole thing becomes 0, right?
Yeah.
So this means that x1 should be 0, x2 should be 1, x3 should be 0, x4 should be 0, x5 should be 1. So at this point, like the point 0, comma 1, comma 0, comma 0, comma 1, this thing is 1. And apart from all these points, it's 0. So now, if I give you this function, let's say the function which we took before. Yeah. Array. Let's consider this function. So can you write f of x comma y comma z in terms of variables? No. Like in terms of variables, I mean like something like this is a valid thing in terms of variables, xy conjugate. So, or even for that matter, like plus this thing. It shouldn't be just one term, but can be multiple terms. So using this idea, can you write this thing? Okay, if this seems harder, let's move one step back and let's just try to write this thing as a function first. Any idea?
We can set f of x. We can have x bar times y bar times z.
Exactly. So we see that this function has value on at only one point, which is the point when x equals to 0, y equals to 0, and z equals to 1. Which means if we consider x conjugate times y conjugate times z, this will be 1 at this point, but 0 at all other points. So now the thing which we had, this. So if you consider the terms x conjugate, y conjugate, z, for this 0, 1, 0, we consider x conjugate, y, z conjugate. And for 1, 1, 1, we just consider x, y, z. And we take sum of these 3 things. See, this becomes 1 at the point 0, comma 0, comma 1. This becomes 1 at point 0, comma 1, comma 0. And this becomes 1 at points 1, comma 1, comma 1. So apart from these 3 points, all 3 of them are 0. So the sum will be 0. So these things are satisfied. And at any one of the 3 remaining points, at least one of them is 1. So the sum will be 1. So this is also satisfied. So using this idea, we can write down a function given values of that function at different points. Is that clear?
Yeah.
Okay, nice. And this form So like you see that these three things are min terms, right? In 3 degrees, all of them. So once we write a function, uh, uh, DNF, this is called as disjunctive normal form. This is basically when a function is written as a sum of min terms. So the function f here is clearly in disjunctive normal form, right?
Hmm.
Okay. Now there is a thing called conjunctive normal form. Uh, there are two ways to view this. So one is you just take dual of disjunctive normal form. Let's just take the dual of this thing here. X conjugate y conjugate z becomes x conjugate plus y conjugate plus z times uh, x conjugate plus y plus z conjugate times x plus y plus z. So it's basically conjunctive normal form is a product of sums of the literals, right? And since this is the dual, this should be the same as the function itself. I mean, wait, same as the function itself, or oh, it should be same as the dual of the function. So like this thing will be equals to 1 0 0 1 1 1 1 0. Okay, sorry, this is not conjunctive normal form of f of x by z, but this is conjunctive normal form of dual of that thing. But
Acha.
conveys the same idea. Like dual is basically like product of sums of literals. Does that make sense? Yes or no?
Yeah, yeah.
Okay. Kachi, is that clear to you as well?
I I think so, yes.
Okay. Yeah, if you have any doubt, just ask. So, let's see if I have that. Hmm. Okay, let me pull up the another way to view this thing, or I'll just tell you. So, see, when we were considering uh, disjunctive normal form, we were basically looking at the ones in the function, right? Like wherever there's a one, we consider that. But in
Hmm.
conjunctive normal form, we have sums of literals. So basically, we have something like, let's say, x plus y conjugate plus z. What can we say about this? This is 0 if and only if x equals to y conjugate equals to z equals to 0,
So
which
X
means it
is
is,
0 and Y is 1.
yeah. So basically, using this thing, we can pinpoint a point which has the value 0. And apart from that, everything will have 1, right? Like this thing, if I said this as a like f of x comma y comma z, then this function is 0 at this particular point, and apart from that, it's 1 everywhere. Okay. So now, by the way, this thing is called a max term. Max term is basically sums of literals where there's a literal for each variable. Similar to min term basically, but instead of product, you just have sums. So now, if you look at the zeros in this function, and then we take product of those points. So like, if I write okay, consider this function for now. Uh, how can I write it in this conjunctive normal form? I can just take f of x comma y comma z as x plus y plus z, right?
Hmm.
And suppose there is a 0 here. And if there was a only 0 here, then I could write x plus
But how will you write this?
Oh, sorry, this should be conjugates here. Yeah. For a zero here, I can like assume there's a one here and zero here, only that. Then you can write this as x conjugate plus y plus z, right? Like this thing will be zero at only this point, right? And now if I take product of these two terms, x conjugate plus y conjugate plus z conjugate times x conjugate plus y plus z. So apart from the points 0, comma 0, comma 0 and uh 0, comma 1, both of them are 1 everywhere, right? So these things are satisfied. Sorry, the other ones. But at these two particular points, at least one of them is 0. So the product will be 0. So this is how I can write the function in a conjunctive normal form. And I can do other terms as well, wherever there's a 0. So does that make sense?
Huh.
Cool. Yeah, you don't really need conjunctive normal form as such for now. But I just did it because it is used and like since we define DNF, I thought why not define CNF as well. Cool. Let's move on to the fun part, minimization of circuits. Minimization of circuits. So, the thing is, whatever this thing we are doing, all these circuits are used in our like computers or stuff. And if you have some like, and the input is in terms of like electrical signals, either one or zero. So, like, let's say we have to consider like in computer machinery, it's considering or of two things somewhere. So what it does is like the uh, yeah. So signal one comes from here, signal one, and signal two comes from here. There's a switch here and a switch here, and this is the output wire. This is the same wire basically here. So is this a good way to? I had something different in mind when I was doing this. Okay. Rather than this, let's consider this thing. Suppose you have a circuit, like here is your battery, and the current comes out, and this is switch one, and this is switch two, and let's say this is your output device. So now, whenever the current comes out, if I see either one of them being closed, the switch is like closed, or both of them, the current will flow through the circuit, right, and travel. So this is how the OR is used in real life, the OR gate. Like whenever you have to take OR, we basically construct this circuit in the computer. And similarly, there's a circuit for AND gate as well. So the thing is, for everything there is a circuit. So whatever thing you're executing, you would want that there are least number of terms in that, right? So that you do not have to use too many circuits. Like if I give you something like XYZ plus XYZ conjugate, then I have to use like one AND gate for this and one OR gate, right? Uh, or rather, okay, this is slightly big example. I'll consider this thing XY plus XY conjugate. So I have to consider one AND gate for this and one AND gate for this. and one OR gate to combine the sum of these two, right? But I can see that this thing is equals to x times y plus y conjugate, which is just x. And I do not have to use any gate for this if I had just noticed this thing. So this is why you want to minimize the circuits, like write it in the least number of terms possible. Like disjunctive normal form takes a lot of terms. Like if I just have to write the circuit x equals like f of x comma y equals to 1 everywhere, if I write in DNF, disjunctive normal form, then this will be xy plus xy conjugate plus x conjugate y plus xy conjugate, both of the terms. Like I do not even need these things. It is just 1 everywhere, right? In real life. So that is why we want to minimize circuits. For those of you who do not understand this, you do not need to. Just know that it is better to write functions in the least amount of terms possible. Like if you see this first function, these has too many terms and it's very messy to write. But you can probably reduce the terms and write it in a smaller format. So is it clear that why you want to minimize the circuits? Or minimize the functions basically. Circuits because in real life it's used in the form of circuits. But let's just say minimize the function for now. Is this clear?
Minimize. I understand how to minimize it, like very clearly.
Oh, sorry. Can you repeat? I could not hear.
I understand how to like minimize it completely. Like, yeah.
You don't
like
understand you're saying, right?
No, I understand it. Just yeah, I
Okay.
understand it.
Yeah, cool. Yeah, now we'll look at some techniques on how to minimize the circuits. Like this was a very basic circuit. Like it was easy to observe that you can combine these two terms. But something like if you have this, there are too many terms, and like which ones do you combine ideally? Right? So for that, we use Karnaugh maps, which are referred to as K maps. So let's just consider a function in two variables, f of x comma y. What we do is we create a grid where this replies x, y, x conjugate, y conjugate. And suppose f of x comma y is x conjugate y plus oh sorry, I wrote it in a bad term. I do not like it this. We write it like this: x and x conjugate in the row, like first row represent x, second row represent x conjugate, and this represent y and y conjugate. Suppose f of x comma y is x conjugate y plus x conjugate y conjugate plus xy conjugate. Then what I do is like these squares represent the terms xy, xy conjugate, x conjugate y conjugate, and x conjugate y. Basically, the product you take in each cell. And you write 1 whenever that terms occur in the expression of the function. So does xy occur? No. Does xy conjugate occur? Yes. So I write 1 here and for other terms as well. And I write 1 here. Now, what I would want to do is I see whenever a row or column is filled in this small case, in this particular case, or basically I just want adjacent things and I circle out those things. So basically I can combine these two things. If I'm circling these two things, I can combine these two things. Like x conjugate y plus x conjugate y conjugate. You can manually say that you can combine it as x conjugate, right? I can just write x conjugate and from here I can write y conjugate. So I can write this whole thing as x conjugate plus y conjugate. But there's one small doubt. This thing, like I can obviously combine the first two terms and get x conjugate plus you have a xy conjugate, right? So how are these two things equal? Like this is a natural doubt, right? Like if you see the representation, this one is circled twice and we have used it twice. I mean, sure, you can show that these two things are equivalent using, what do you say, truth tables. But let's just do it in a clever way. See, we have this x conjugate y plus x conjugate y conjugate plus xy conjugate, right? And So I told you in the beginning, it's wise sometimes to consider A as A plus A. Okay, what's this? Yeah. So it's wise to consider this as A plus A. And then these two terms will give you X conjugate and these two terms will give you Y conjugate. But the function is still same. And this is exactly what we got from minimization, like using the K-map. Like we do not have to think of this clever step. The K-map already does that for you. So is it clear that why is K-map good? Yes or no?
Yes.
Okay. Yeah. So this was a K-map for 2 degrees. Now, how do we do it for 3 degrees? So all right, hold on. Yeah. So in 3 degrees, we have X comma Y comma Z, right? So we consider uh 2, 3, 4, 5, 6, 7. So you consider X and X conjugate in the rows, and in the columns we consider. Array, I drew too many. Sorry. YZ, YZ conjugate, Y conjugate Z conjugate, and Y conjugate Z. Then this square represents XYZ, X conjugate YZ, XYZ conjugate, so on. One thing to notice is you have to be clever and like clever in the way that this if this term is YZ conjugate, right? Like the order of these 4 terms should be this way, or a cyclic shift of those. I'll tell you why, but make sure that the order is important in this. Like X and X conjugate, you place however, but it does not matter. So suppose you have this function. Uh, yeah, go on. Okay. In this case, like suppose you have a 1 and 1 here. You can club those 2 ones because the 2 ones represent XYZ conjugate plus XY conjugate Z conjugate. So you can take XZ conjugate common and this is Y plus Y conjugate. So this can be written as XZ conjugate. So if you see a 1 cross 2 rectangle or a 2 cross 1 rectangle, that is good, like a adjacent rectangle. Another thing which is good is if you see a square, small square, like if these are ones, then uh like this is like XYZ conjugate plus XY conjugate Z conjugate plus X conjugate YZ conjugate plus X conjugate Y conjugate Z conjugate. So the first 2 terms you can combine and write as XZ conjugate, and the third and fourth term you can combine and write as X conjugate Z conjugate, and then you can combine these 2 terms and write it as Z conjugate. So if you see a square, that also helps in minimizing. That is good. And another thing which you can see is a whole column filled. Sorry, a whole row filled. Like if all these 4 are ones, then this thing will just be X conjugate. Like you can try to do it manually, like YZ plus YZ conjugate combines and gives Y, and this gives Y conjugate. So yeah. But the thing is, like we see that these two can be adjacent, which are good. These two are good. These two are good. What about if you have a 1 in these 2 squares? You can combine those two as well because this will be XYZ plus XY conjugate Z. So this will be XZ. Helps in minimizing. So this adjacency is also defined, by the way. Like a better visualization of this is consider a cylinder. Like just roll this thing. And this cylinder has 8 sides, no? I mean 8 faces, whatever. 2, 3, 4. Yeah. So if I roll this, then the front face here can be x, y, z, and then the face on the back will be x, y, z conjugate. The face here would be x, y conjugate, z conjugate, and the face in the front here would be x, y conjugate, z. So like everything is adjacent, right? Like even x, y, z and x, y conjugate z, these two things are adjacent. It just in 2D it does not seem so, but in many dimension you can see the adjacency clearly. So in this case, whenever you see like a 1 cross 2 rectangle, 2 cross 1 rectangle, 4 cross 1 rectangle, 1 cross 4 rectangle, 2 cross 2 rectangle, uh, and like the whole thing, 2 cross 4, which is just identically 1, then you know that there is some sort of minimization which you can do. So is this clear that how we do it for 3 variables? Yes or no, people?
Yeah, yeah.
Okay. So as an exercise, oh yes, one more thing. I said that the order here matters, right? So why is that? Suppose I switch these two terms. I write y conjugate z conjugate here and yz conjugate here. So now suppose I have ones and ones here. Then these two terms will be x, y conjugate z conjugate plus, forget that these exist, plus x, y, z conjugate. Can you minimize these? Oh, surprisingly you can. Array, there was this part, some order in which you cannot. Let me think. Okay, yeah, in this order only. Consider these two. Suppose these two are one. These two are adjacent, but you cannot combine them because they are y z conjugate plus y conjugate z, which is bad. You do not want such things happening. So this is why the order matters. And the order is not hard to basically like think of. Like, you don't have to memorize the order. But the way I like you can just memorize it by a trick. It's just yz, take conjugate of one, take conjugate of other, and then the remaining term. Yeah. Slightly stupid, but this is how you do it. Cool. So now do this example. Write this in minimized form. Let's see. XYZ plus XY conjugate Z plus X conjugate YZ plus X conjugate Y conjugate Z. Write this in the minimized form. Uh, do not speak out. Try it for like 2 minutes and type your answer in the chat. Yeah, Shrish, that's correct. Other people, it will be nice if you answer. I'll wait for 2 minutes. Yep. Okay, so if you see, like this thing is basically like you have one here, one here, one here, and one here. And then you can just see that this is a square. Like two things from here and then two things from here. Like these two are adjacent, right? I mean, you can write if you want for visualization YZ here again, and then this will be 1, 1. So this is a square. So you can combine these, and this will be like x and x conjugate cancel because they are in two rows. So this will be y conjugate z plus yz, which is just z. So yeah, good. Now we can extend this to 4 variables as well. And the idea for 4 variables is similar. Basically, you take a 4 cross 4 thing. Suppose the variables are w, x, y, z. So here, just like 3 variables to write y, z conjugate, y conjugate, z conjugate, y conjugate, z. And similarly, here you consider w and x. So you have wx, wx conjugate, w conjugate x conjugate, w conjugate x. And here you can have stuff like a 1 cross 1 rectangle, which is just a unit square like this, which is useless. 1 cross 1, 1 cross 2, 2 cross 1, 2 cross 2, like this thing. You can also have 2 cross 4, like this, and then 4 cross 2, and a 4 cross 4, which is just the whole thing. And notice that this square is adjacent to this square, and this square is also adjacent to this square, just by cyclic shifts. And then you can minimize the stuff. Like the way to minimize is, formally speaking, you would want to make as many like small number of rectangles, but large size rectangles. So like if you have something like 1, 1, 1, 1, 1, 1, you can make the rectangles like this as well. This is one rectangle, this is one rectangle, and this is one rectangle. This takes 3 rectangles. But optimally, you can just do this. Just take this as a rectangle. And this is valid, right? Because we discussed about overlaps. So this takes 2 rectangles and covers all the ones. So that is how you do minimization. Okay, so let's do some examples of minimizations using K-maps. Red paste it there only. Try the first question. And I'll also try meanwhile because I haven't done it. Preferably do not see my work because that will give you more intuition on how to do this. Try it for 2-ish more minutes, then we'll see. But I'm not marking it. I think I sort of see it. So yeah. Shresht, we are trying problem one, minimization of this function by K-map. So try to solve that. Okay. Bye. Oh yeah, sure. I'll wait for 1 more minute for people to do this. Okay. Did anyone get anywhere? Any ideas which terms we should combine? Okay. So we see that these two are neighboring clearly, and then so are these two things, and these two as well. Notice that odd number of side rectangles we do not want because they do not work. Like if you had 1, 1, 1 for these three, then taking these three will won't help. You can try to figure out why. So we only take like powers of two as the sides. And then you'll have these two as neighboring. And then this will be left alone. And you can check that there is no better way to do this. I mean, there can be equally good ways, but not a better way. So let's see how we can write. So you can write the single term as itself, w conjugate x, y conjugate z. These two terms will give you plus w conjugate x conjugate y. These two terms will give you wx y. These two terms would give you uh, wy conjugate z conjugate, and these two would give you wx conjugate z. So I hope this is clear. Let's just do one more problem. Let's do part B. This part we are doing. Hmm. So for this problem, we can see that there's this square in the between, and this whole column is filled. And now this one is left alone. But notice that instead of leaving this alone, it's better to combine these two terms. Because once we left it alone, that term would come out as W x conjugate YZ. Whereas once we combine these two as well, we'll get W x conjugate Y. And since we need to reduce the terms, this is better than this thing. So overall, this would become Y conjugate Z conjugate plus X conjugate times Z conjugate plus WX conjugate Y. So yeah, this is how we minimize this circuit. So is Karnaugh maps clear? For more than 4 variables, this is not feasible to do. But for until 4 variables, is it clear? Okay, I'll assume that it is. I was planning on doing Quine-McCluskey method if you had time, but I don't think many people are there, so there's no use of doing that. I'll just not do it. Okay, just tell me if people would like to know the proof of duality principle. If you want to do that, then I can prove duality principle. Otherwise, you can end the class. Okay, I'll end the class then. But for people who are viewing the recording and who want a hint, for duality principle, try to consider this thing. Suppose you have a function f of x1 comma x2 so on till xn. What happens when you consider x1 comma x2 so on till xn and complement of this whole thing? What happens when you consider this? And you might want to look at De Morgan's laws to prove duality principle. It is not hard. It is just basically saying that x conjugate times y conjugate is xy conjugate is x conjugate plus y conjugate, and x plus y whole conjugate is x conjugate times y conjugate. This is what De Morgan's law say. So using these De Morgan's law, try to think what happens with this thing. And then you can prove the duality principle with some more effort. Quine-McCluskey method, if people want later, I can record it and upload on YouTube. So let me know in like Discord or comments. But yeah, I'll end the class.